Sorry about that. So we're talking about DAGs, just to review. And so here's a DAG because it's a directed graph. It has no cycles in it. And on a directed graph, you can identify sources and sinks. So a source is a node or vertex with all the directed edges or arrows pointing away from it. So C here is a source. Now, if all the arrows point towards a node, that's a sink. So a sink is a node with all arrows pointing toward it. Okay, so that's what you mean by sources and sinks. So this graph has a source and a sink. Now let's look at a directed graph, because any directed graph can have sources and sinks. So let's look at this graph. Now this graph has A has an arrow going in and out, B has an arrow going in and out, C in and out, D in and out. This graph has no sources and no sinks. On the other hand, it's not a DAG. It's not a directed acyclic graph because it has a cycle. For example, it has a simple cycle. It has several simple cycles: A, B, D, C, A, B, D, C, A, B. And the fact that it's going to have 4 simple cycles. Okay, so it has 4 simple cycles, so it's not a DAG, has no sources and sinks. So now you can have a directed graph that does have a source or a sink. So for example, here's a graph. It's not a directed acyclic graph because it has a cycle B, C, D, B. However, it can also have a source. So it can have a source but no sink if it's not a DAG. And also, if I turn this around, you can see it could have a sink but no source. So it turns out that DAGs are special. A directed acyclic graph always has at least one source and one sink. Okay, so it always has one source and one sink. And that's what we saw up here. Not that one, but this one here. We have a source and a sink. Now, there's something else that's special about directed acyclic graphs. They have what is called a topological ordering. You get, I mean, it's called a topological ordering, and this may seem like a frightening word, but it doesn't mean, it's just a name for here. We're not actually interested in why it's called a topological ordering. So we're just going to say DAGs in fact always have. In fact, what it's going to be is a graph is a DAG exactly when I haven't defined yet what this is, a topological ordering. Okay, So a graph is exactly when it has a topological ordering. Okay, so for example, if it's a DAG, it has topological ordering. If it's a topological ordering, then it's a DAG. Okay, so what is a topological ordering? Is a sequence or list of all the nodes or vertices, if you want to call them that, in a graph. It's not necessarily a path because they're not going to be, it's all the nodes so that it doesn't have to be a path. Okay, so it's all the nodes with the following restriction. Such that if that for every, it's hard to set, it's hard to describe in words, such that the um, the initial node of an edge is to the left. I'm thinking of the list written horizontally, to the left of the final node of an edge. It'd be easier to see. It's harder to write in words than it is to understand. Okay, so what I mean by this is, if this is an edge, then A is the initial node and B is the final node. So, for example, a topological ordering for this one would be AB, where A has to appear before B. So in some sense, if I drew arrows here, they would always point from left to right. So it's sort of like we're always starting. Now let's look at some other graphs to see. Here's a directed acyclic graph. Now topological, it has a couple of topological rings. For example, A, B, C, D, and A, C, B, D are both topological orderings. You can see because A goes to B, left to right, B goes to D, left to right, and A goes to C, left to right, and C goes to D, left to right. So the initial nodes for every edge are to the left of the target node for that edge. So if I start here and follow an edge, I can always, it's sort of like I'm never going to have to go backwards. Now you notice that these are the same, except that C and B are not really ordered, because C, there's no way that I can sort of say, if you think of the relationship as before, A is before B, B is before D, A is before C, and C is before D, but B and C aren't ordered in any way. And that's why you have different topological orderings. Okay. So now, because I found the topological ordering, I know that this is a DAG because it has no cycles. So if you ask, does a directed graph have a cycle? You could attempt to, and it was complicated. You could attempt to, maybe the cycle is hidden somewhere in there. Then maybe you can check if you could construct a topological ordering, then you would be able to determine whether it was a DAG or not. Now, it turns out there's an algorithm, and that's what we'll sort of finish with today, is the algorithm for calculating let me draw a graph, and we're going to show you the algorithm for writing down a topological let's see. Okay. This is A, B, C, D, E, and F. Okay, so topological ordering has to be a sequence of all 6 nodes. And here's the idea. Well, it's based on the result. If I remove a source from this graph and all the legs connected to it, the result is still a DAG. So if I remove a source and all the edges are connected to it, the remaining piece is a DAG itself. Now, every DAG has at least one source. So I can do the following in a loop, sort of repeatedly. One is remove a source and connected edges. Okay, so for example, here I can see that A is a source. So now I am going to, let's see, I'm going to then remove it. And that will be the remove a source, that source will be the first one in so here we'll choose A to be the first in our list. Okay. And then we will X out this node and cross off this one. So what I'm doing is then what's left over here after I've removed A and its sources is itself a DAG. Because it's a DAG, it's guaranteed to have a source. In particular, it has 2 sources. For example, in this green, in the portion circled in green, D is now a source, as well as B is a source. Okay. So then what I do is remove a source first, and then I just keep doing that. Repeat. Okay. For example, let's say that I take B off. So I'm going to put B here. Now that means I get rid of B and all the connected edges. So what I'm going to have left is this piece here. Okay. Now that's a DAG and it has 2 sources, C and D. So I could choose D. Well, let me use a different color. Let's see. There. Orange. Okay. So then I could choose, say, D. And then that would leave this piece as my directed acyclic graph. And then I could choose, say, C. Well, I can just do that. Then I'm going to end up with then E and F. So there's my directed acyclic graph. And you can see how each time you remove a node, put it in your list, remove a source, put it in your list. So all the way down, you're sort of paring it down. Now, because I found a topological ordering in this graph, that means that it is a directed acyclic graph. And that's it. That's the algorithm for finding directed acyclic graph. So some of the exercises on regex, I'll give you a graph and ask you what's a topological ordering. And so that's one of those tasks that you can do. So there's a set of tasks you can do with that topological ordering, because it's explained here sort of. Okay, and then here's the theorems. And there's 2 more topics we have in this section, one dealing with Euler paths and Euler circuits, and the other dealing with vertex colorings, chromatic numbers, clicks and some other details, but those terms all deal with undirected graphs. So what we have here is you have to be able to identify a graph, see when it's directed, undirected, whether it has paths, simple paths, cycles, simple cycles, whether it if it's a directed graph, whether it is a DAG or not, whether it has a topological ordering or not, and given a graph, construct a topological ordering. Okay, so let me